And then here we can even simplify this. Since of this we have a constant here. If we do an additional transformation, I define a new variable eta here, and the eta and y have this relationship, and this phi and f have this relationship. Okay, I can change y and f function here. This is y and f function here, and change to eta and phi. Okay, and I can this solution, this carbon equation can even be simplified. Okay, become like this. So this equation becomes so-called a dimensionless problem. That means we don't have any unit or dimension. Here we have a dimension, right? Here we have dimension. So this is a dimensional equation. So okay, here we don't have any dimension here because all the constant here, okay, don't have any dimension. Okay, so this is non-dimensional. Okay, it's non-dimensional. So we have this more okay. We call this non-dimensional for this physical problem. Okay, by scale, if you can scale like this. Okay. So as you can see, we did that before, right? We did that before. Y divided by this is what? This is a boundary layers. This is the viscous layer, right? Y, when you have a y into here, we have a viscous layer. So this is a y divided by viscous layer or diffusion layer, and then give you the non-dimensional eta. And this is another function is try to change our velocity by non-dimensional by this, give you the non-dimensional velocity phi. And so this will be dimensionless potential, dimensionless equation or problem. And this dimensionless problem should be satisfied the boundary constraint like this. Okay. Okay. So that will, so until right now, okay, we can using our so try to solve this problem, okay, and since this is a Olden differential equation problem, and Olden differential equation problem, we have a lot of the numerical method, easy numerical method. You can run in 1 second, you can get a solution. Okay, like a Runge-Kutta. Have you heard about that? Runge-Kutta method. 如果你们有学数值解的话，一个 ODE 如果你是哪一边多少阶的 ，any order of ODE is very easy to solve by numerical. Okay, we can use it to Runge-Kutta. 你写错，忘了是 KUTA KUTA. Runge-Kutta method. Okay, you can check. Okay, very easy. Within 1 second, you can get all the solution for this equation. So instead of using the analytical solution, we need a computer to help us to solve this. Okay, but it's not hard. It's not like a CFD. CFD you're using the CFD is a more non-linear equation. Here is a linear equation. Okay, linear equation. We have exact solution for this. Okay, very precise solution for this. Even we're using a numerical. Okay, and then we can plot this flow like this. Okay, so this is we can find out this phi. Okay, and this phi can be solved like this. This is a solution look like this. This is a phi prime, and this is our eta. So we have this. When eta increase, that means y increase, and then our phi prime will be increase like this. If you plot this solution form like using the numerical method to solve it. And what's the f prime? Phi prime here, as you can see here, if you go back to our phi prime is here, right? Phi prime is here. So the phi prime times 2us give you a u velocity. Okay? And v is minus square root of 2 mu u times our phi. And this is pressure field. It will become like this. Okay? Once you find the phi prime, phi and phi prime, you can find out the velocity u, v, p here. Okay, so that from the numerical you can find the phi and phi prime. Okay, no problem at all. So this is one plot is for the phi prime over eta. So this is a phi prime in the vertical axis here, and this is eta. Eta represents the y, right? It's a scaling with a y. Okay, so this is y equal to 0 is here. Okay, the near boundary, And what's the phi prime? Phi prime is related to u, right? U velocity. So u velocity is increase, and then approach to what? Approach to 1 when phi. Okay, that satisfies our boundary condition because when it's approach to 1 here, as you can see here, if you go, I should copy that here. Okay, phi prime equal to 1, our u equal to 2ux is what? It should match back to the potential solution, potential flow solution. Okay, phi prime. So we can find out phi prime is equal to 0.99. 0.99 means phi prime and compare with our potential flow solution, only small difference, 1% difference. Okay, so at this occasion, we try to find the eta for phi prime equal to 0.99. That means there's a boundary between what? Boundary between our viscous region and our potential region, right? Remember that the picture like this. When V prime, right? When at this location, this is interface between the viscous region and this is our potential flow region. And how far is this here, location here, should this viscous region reach and match our potential flow region? And phi is equal to what? Is equal to what? Phi prime equal to 1, right? And our eta equal to, according to the solution, at this location, eta equal to 2.4. Our phi prime should be almost 1% different with the potential flow solution. So we can define this eta equal to 2.4 is a boundary region, right? Boundary layer thickness. Okay? So delta 0.99 represents the eta equal to 2.4. So eta is equal to this. So when eta equal to 2.4, this eta equal to 2.4, y equal to delta 0.99. So as you can see, 2.4 divided by this value, square root of mu 2u, give you the boundary layer, the viscous layer thickness. Okay, from this viscous layer thickness equation here, what can you conclude? When I have a flow, much higher flow, U is much higher, what happened? Our thickness become smaller, right? Depending on your uniform velocity, how the impinging flow velocity. Okay, your impinging flow velocity is higher, your thickness, or stagnation point flow is thinner. Okay, 当你的往下冲的流速比较快的时候，那一层 viscous region 或者我们讲 boundary layer region， 它就变得比较薄。Okay， 这从这地方可以看得到。So viscous effects are confined to the boundary layer adjacent to the solid wall, right? Solid surface. When U is higher, that means our delta 0.99 is smaller. And U also can be represented the landscape divided by T. And landscape divided by T, as you can see here, okay, this is mu divided by 2U, okay? And then give you what? Give you the so-called mu T. Square root of mu T is what? Square root of mu T is, this T is the time, right? And this give you the delta. Remember our viscous region, okay, in in the Stokes first problem or Stokes second problem, our viscous region is scale with what? Scale with this, right? Scale with this. So this viscous, how viscous transfer momentum, how far they can transfer the momentum, is a mu times a time. Take a square root, give you the how far the momentum can be transferred by the viscous effect. OK， 也就是说，这个 mu 乘以一个时间开根号就可以告诉你，你这个 viscous 经过 viscous 去传递这个动量的时候，它可以传多远，大概传多远，它的厚度大概传多远。Okay, so that's a very important length scale, okay, in the viscous effect here. Okay, so this is a kind of conclusion we have, okay, for the stagnation point flow. Okay, I think the next, okay, we still have two physical problems. Okay, this is the last two, okay, for the chapter 7. 我们还有两个 stagnation， 还有两个物理问题还要解。So this is called a flow in the converging and diverging channel. So this is a convergent, this is divergent channel. So this section here is called a convergent, like a narrow, right? We have a narrow flow, that's me. And this channel here is what? What? It's a, we call this kind of flow is what? What is flow here? 你们知道这叫什么流场？这叫什么样的一个？这里 when flow from a small area to a bigger area, what kind of the flow is this? We call this flow is what? It's a diffuser. 扩散器 okay, diffuser. And we in the fluid mechanics we're using the narrow, convergent narrow or divergent narrow or the convergent channel we call the narrow, and the divergent channel we call the diffuser a lot. Okay, a lot. Go to the jet engine again later. Okay, you will see a lot of region with a narrow convergent channel with a divergent channel. When do you need the divergent channel? When do you need that? 你什么时候？我们什么时候会放这样用这个东西 ？Pressure what? In what? Say again. I didn't catch.
Pressure recovery.
Yes, pressure recovery. Pressure recovery means you want to increase your pressure. And increase your pressure, typically we would like to slow down our velocity. Okay, that's a diffuser most of the time using. And narrow, vice versa, we like to increase our velocity, right? And then decrease our pressure. So diffuser use what? Use in, again, in the combustion chamber. Combustion chamber, with the flow before the combustion chamber, we should increase the pressure but slow down the velocity, right? Because we would like to ignite, okay, the combustion happen. So the flow cannot be too high, okay? However, our pressure should be increased through the thermodynamic, okay? So before the combustor in the subsonic flow, we always using a diffuser here, okay? And when do you need that? When do you need this? Narrow. 什么时候我们需要 narrow？ 你们知道？ Go back to the jet engine again. Okay, you see the last one. Okay, I just mentioned. Okay, there's a one engine. Okay, and J79. Okay, J79 引擎. Okay, that's for the fighter F104. Okay, and when I was in the military service, I try to I disassemble every engine like J79 and J85. Okay, before, so I know detailed information inside that engine. And then the afterburner, if you see the afterburner, there's one section, right? And we have narrow. Okay, and this narrow with a controllable variable, like so the area here, the narrow usually will try to increase the velocity to generate thrust. Okay, so we have in the narrow, the end of the jet engine. If you're after the afterburner, you may use in the narrow to increase your thrust. So we like to understand when the flow, okay, flow into this convergent channel and divergent channel, and how this physical problem can be solved. Okay, again, we can using so-called polar coordinate system. And polar coordinate system, this is a continuous equation. This is in r theta direction. Okay, and in the polar coordinate system, as you can see, we plot this like this. This is our origin here. So this is r direction. This is r direction, and here is a theta direction. So boundary here is all r direction, right, along the r direction. So for the fixed theta, so this is theta equal to one fixed number. Okay, depend on this half angle here. So for this kind of flow here, okay, we have a UR, U theta. UR mean the radial direction flow, and U theta mean the sequential direction flow, right? And then for this kind of flow here, we take the V theta equal to 0. V theta equal to 0, we don't have any sequential flow. We only consider the radial direction flow, R direction flow. So we can simplify this carbon equation. So V theta equal to 0, right? V theta. And this RVR should be, take a derivative, should be equal to 0. That means RVR should be a constant. So RVR should be, when R times VR is a constant, mean VR is a function of what? It's VR is what? It's a constant over R, right? Constant over R here. And this constant is maybe is a function of theta. Okay, so this we use the F theta as a function here, and this is our constant, mu, okay? And then divided by R, this is our VR solution form for all this flow field. Okay, so from the continuous equation, we know the flow field in the R direction should look like this. Okay, so we introduce another function called F. So this is from, if you go back to the original polar coordinate, so you have the R, theta, Z direction, 3 direction coordinate. And then U theta equal to 0. And UZ, because we don't have any Z direction flow, U theta equal to 0. And then we negate our body force, and U theta equal, this is U theta equal to 0, right? So the solution we have, this is steady state solution, so this term should be also dropped. So we only have this term, and this term, and this term, these 3 terms left. Okay, and this is Laplace should be represented like this. Okay, so our carbon equation, okay, once you're using this, and then this Laplace here, and then drop all the term, in R direction momentum equation should reduce to this. This is theta direction momentum equation. Should be able to do that. Okay, if I give you the complete this, you should be able to simplify your physical problem to this. Okay, you should try it and then try to do that. Okay, by assume U theta equal to 0. Okay, and you can get R momentum equation, and this is theta momentum equation. Okay, so here you can do that. Okay, and then by plug into this solution form, right? We already from continuous equation, our VR should be equal to this solution form, mu F theta over R. By using this into our carbon equation, all the VR, okay, and VR, partial R. So what you try to do is try to find out the VR, partial VR, partial R. Okay, this is our R direction momentum equation. This is our theta momentum equation. This is our solution form, right? We just mentioned. Okay, so I try to find out partial VR, partial R. Try to find out this. Okay, this term is here, and try to find out this term here. R times partial VR, partial R. This is R times partial VR, partial R. And take a derivative with R. This is so I try to evaluate this is here. Okay, and I also try to evaluate this partial VR, partial theta. Partial VR, partial theta is equal to this. And then finally, I need to do this, right? Partial square VR, partial theta square should be equal to this. So from here, I try to evaluate every derivative I need. Once I do that, I plug back to this solution, this carbon equation, and then this is R momentum equation. Okay, should reduce to this, and now theta momentum equation should reduce to this. Okay, 这是带进去。Okay, and then what I try to do is try to using this partial P, partial R, and partial P, partial R, and rearrange this equation. And so this is partial P, partial R. By using this equation, I can have this. By using this and this, right? And I can have this here. Partial P, partial R should be equal to this. And from here, partial P, partial theta, right? Equal to 0. So this partial P, partial theta should be equal to this. Okay? So from this equation, what I try to do is I try to partial P, partial I take additional partial p partial this equation to partial theta. And for this equation, partial p partial theta, I take an additional derivative, partial p partial r, right? So this is take a derivative with r, this take a derivative with theta. So this will be the set. Okay, and so this term should be equal to this term here. So I have this solution. I have this equation by using this and this. This is okay. By combine r direction momentum equation and theta direction momentum equation, I have this carbon equation. Okay, after simplify, I can get this F triple prime, 2FF prime, 4F prime. This is reduced to this simple form carbon equation for F function. Okay, so again, all this, I try to do everything like here, try to find out, okay, our F function should satisfy this carbon equation. Okay, and then the rest I just try to using the mathematically to solve this equation, right? Because once I find the F, and I can find, once I find the F here, I can find the VR, right, already. And the VR give me the velocity flow field. Okay, and we should keep. Okay, time running out. So I will stop here. Okay, next week, next week. On Thursday we will start from here. Okay, we will start from here to solve our this physical problem by using this equation.